Anderson, kind of introduction. First of all, I'd like to thank the organizing committee and especially, of course, Indri-san for giving me an opportunity to present here. Very nice workshop. I'm very interested. I'm very excited. So, okay, but as Indri-san said, the time is a little bit behind, so I must speak to move to my lecture. So here is my. Can you see? Indri-san, okay?
Yes,
Okay.
we can see.
Yes.
Okay.
So I'm Nobuyuki Ichikuni from Chiba University, and the title is as Indri-san explains. So now we to hear my today's topics. Today my presentation topics is here about the introduction part and the explanation about the exafs and the application of the exafs to solid catalyst and summarize it. Okay. Now move to the first part of the introduction to Chiba University. And important point is there and me. A little bit to introduce myself. Can I introduce myself? So I graduated from the University of Tokyo in the supervised by Professor Iwasawa. And now at the graduation, I have a job. Luckily, I have a job at the Chiba University and working at the Chiba University. And my specialty is, as explained in the recent, then catalysis. Of course, especially for the characterization by using X-ray absorption techniques. Here is my just a hobby of the learning, no problem. Okay. Of course, the Chiba University, Indri-san knows very well. However, not so much people know the Chiba University. So I must introduce where is the Chiba University. This is, of course, as you can see, the Google Maps take in Japan. So the Japan is the center part. Of course, if you take us open the Google Maps, your country is the center side. So it's of course a Japanese. I take a picture of this. So we'll focus on Japan is the important point. So center. Okay. Here is Japan, Indonesia, and of course this workshop will correspond to from UK and Korea and I forget some of the part of the Canadian or Australian. I forget. Sorry, I'm sorry, forget it. Okay, move to Japan. Here is the center of this map is Japan, and it's expanded view of the Japan. There are so many famous places like Kyoto, Osaka, Yokohama. Of course, Tokyo is the capital of the Japan, and Sendai, Hokkaido. Hokkaido has a very beautiful eating and a very beautiful natural, and Yokohama is the largest city, Osaka. However, what is Chiba? We can't see any Chiba. So move to here, like close to this center of Japan. Here is Tokyo, and Chiba is here, about 35 kilometers from Tokyo. And this is the area of the Chiba Prefecture. Right side is the Chiba Prefecture. And if you come to Japan, there's almost all the airplane is the largest one is Narita Airport. Narita Airport is not in Tokyo, but Chiba. So if you come to Japan at the Narita Airport and want to go to Tokyo or somewhere in Japan, first not take a bus. Please take a train. And so train will come like this. So trains by Chiba, passed by Chiba. So please get off at Chiba, and you can see a Chiba University very well. So it's close to the. In that meaning, Chiba University has opened to the world. I think so I'm representative for the Chiba for the international university. Just my hope. Okay. that is not a good point, but our university is a little bit larger one, I think. And we have 10 undergraduate schools, like Faculty of Liberal Arts and Sciences, letters, law, politics, economics, education science, engineering, of course, horticulture, medicine, pharmaceutical sciences, nothing. And 17 graduate schools, like here. And 4 attached schools. So many faculty and schools. Yes, it's our, this is so we can proudly say it's university, not college. Okay. And how many students and how many staffs? And students is the 10 undergraduate degree student is 10,000, and master course student 2,000, doctor course 1,000. So much students here, and staffs is academic staff is about 1,300, and administrative staff is 2,000. Gender balance is not good at the academic staff. However, all of the staffs summarizing is the gender balance is almost balanced. That is a good point, I think. I hope the gender balance is okay at Chiba University. Okay, and as I introduced, my university is opened for near the largest airport in Japan. So in that meaning, our university wanted to become an international university. So we tried to open many universities and institutions for the foreign countries. So we have agreements with partner universities and institutions as follows. 261 university level exchange agreement was held between 260 universities, and the faculty level exchange agreement was 220 at this May or later. I just forget it. And how is the international student? About 2,300 students is here, and was one of international student was, of course, English. Yes, and we wanted to go student to our upload. So the 2 years before going upload was only 830. That is not a international. Just what a pity. However, we decided to every student must go upload during 4 years, or the Masako student to do for 2 years. They must at least one time to go upload. That is our university's program. However, these COVID pandemic, so we can't proceed such a program. However, in the near future, we can send a student easily for go upload. I'm willing to go there. They have a wonderful and learn more at the foreign countries. I will imagine that many of them are my students in my laboratory can go to Indonesia, and so learn many culture and learn discussing with each other to elevate their skills. Okay, that is our university's target, of course. So, and back to the scientific field of the topics. Okay, what is X-ray absorption fine structure is? However, the X-ray absorption. So we need to know the X-rays. X-rays, of course, interact with the matter. Once X-ray was injected in some materials and some matter, so many phenomena are occurred. One is almost all the part was transmission X-ray, and if the material is regulated structure or the long-range order structure, having a long-range order structure, then the diffracted X-ray was observed. Of course, there is fluorescence X-ray was observed, and in some cases, Thomson-Compton X scattering was observed, and yes, the strong X-ray was injected, then the photoelectron and the OJ electron was emitted. And ion, in some cases, ion was rejected, and of course, a heat. So many phenomena was occurred by injecting the X-rays, but X-ray absorption fine structure, X-ray absorption spectroscopy use this incident X-ray intensity and transmission X-ray intensity is an important point. And one case is fluorescence X-ray was used to measure the EXAFs. However, this is based on the transmission X-ray. Okay. The meaning, so this case is X-ray absorption and the emission case. I explained about the fluorescence X-rays was applied for ZAFS measurement in some cases. However, that is related to the X-ray absorption. So in some cases, fluorescence X-ray is one of the key measures of the absorption spectroscopy. So we can use some cases, fluorescence X-ray was applied for the X-ray absorption fine structure. Okay, what is the EXAFs? The phenomenon is here. The photon energy was increased here, and the y-axis is X-ray absorbance. Absorbance was gradually decreased as the energy was increased. And so at some point, at this point here, like here, the sudden increase of the absorbance, and in subsequent region, you can see this oscillatory part. This energy point was so-called the absorption edge. And you can see this oscillatory part. This phenomenon can be roughly explained as the interference between the outgoing electron and the incoming. The incoming electron was where has come from. These are scattering atom. Adjacent or the near neighboring, the atom can scatter the outgoing photoelectron and backwards. Then the incoming electron, outgoing electron, both has a wave, so that was easily interfere each other. So it's schematically understandable, this picture, that is this oscillation. Intermeaning just difference, modifying as existing the scattering at, the more probability was modified. That is a true meaning. However, this phenomenon roughly explained is very understandable, I think. So, okay, and I just say that ZAFS is X-ray absorption fine structure, and there can be divided in two parts. What is first part is around edge, about 50 or about 100 electron volt of the edge region. This is a so-called X-ray absorption near edge structure. I used calling the Zanes. However, some person pronounce the Zanes or Xanes, but I prefer the pronunciation of the Zanes, so I called it Zanes. And after the edge, about 1,000 electron volt is very wide energy region is with the oscillatory part. This is an extended X-ray absorption fine structure, EXAFs. ZAFS is divided into Zanes and EXAFs. While you separate or divide the two regions, because analysis technique is different, is one reason. And of course, the important point is the obtainable information is different. The Zanes near G region can provide the electronic state of the absorbing atom, and of course, the symmetry of the absorbing atom. On the other hand, EXAFs provides information about the scattering atom. It means near what kind of atoms are near the dissolving atom. And there is a scattering atom, what is and how many, how many now atoms here, and how long, how is the distance between the absorbing atom and the nearest atoms, scattering atoms. That is obtainable information by analyzing exas. This is a typical procedure protocols for the ZAFS analysis. First, you get such a spectrum, this case, and this is a slope. This has a background slope, so we're using a background remover to easily get the information about the exact region, and normalizes the edge height. And this is electron volt. X-axis is electron volt, photoelectron energy, converted into the wave number, and extraction of the exact oscillation. In the neural cases, the K wave numbers weighting. K cubic is the usual case. Is K cubic ZAFS oscillation was presented here. And this exact oscillation was transformed, fully transformed. And you can get like this radial distribution functions. This case, about here, you may have this system around 2 angstrom. There must be some atoms, and about 3 angstroms, there must be another atoms. So, what is these atoms here? So we in many cases, analysis can be done by a curve fitting. Firstly, selected this large peak and back Fourier transform, inverse Fourier transformed here. And we calculate this oscillation by using some theoretical analysis or experimental analysis. So you can get these fitting. This peak is main peak is this case is manganese oxide ZAFS spectrum, and this main peak is manganese scattering. This the shorter one is oxygen scattering. So after the curve fitting analysis has been done, at this stage, the coordination element, coordination number, coordination distance, and absorption elements are obtained or determined. That is a typical procedure of the exact analysis. Okay, what is the characteristics of that? The point is this 4 part, no need of long range order. So we can get amorphous materials applicable for the amorphous materials. And this is a strong point compared to the XRD. XRD must have a long range order. So catalyst surface is usually doesn't have a long range order, so we can't get the any information from the XRD. In such cases, that is a strong, powerful tools for analyze it. And this is based on the X-ray characteristics, strong transparency ability. So any atmosphere is okay with gas, under gas or with concomitant with liquid is okay. So this can be applied under reaction conditions. Any phase is of course okay, solid and liquid, and the gas is a very tiny part. So I don't need to use the gas phase exact. However, theoretically, we can get the information of the gas phase. But fourth point is important. This is also the element selective analysis. That is applicable for the multi-component. In many cases, solid catalyst has active species on a oxide support. So there must be a 1 active metal and oxide support metal and oxygen. There must be at least 3 elements in this case. but we can get separately the information. This is a multi-component system. Okay, and move to that, the information about it, the need of long-range order. Yes, I explained about this case. Fraction is must be a long-range order. However, the case is no need of the long-range orders, so they're applicable for the small particles. Okay, and the second point written in the fourth point, the element selectivity. This is the spectrum from the photon factories synchrotron radiations, the photon factories energy spectrum. This case is not important. Important point is bottom part. Here, I show some of the element in the titanium, copper, bromine, niobium, rhodium, silver. This is the K edge, and absorption edge is very different, like this. And in photon factory at Tsukuba in Japan, you can get only about this region, or the some of the PF advanced ring, PF air ring has a more strong beam for the higher energy. However, if you want a high 40 to 50 kilo EV, then you must move to a spring rate at Japan. Also has a strong synchrotron radiation facilities. However, in such a higher K edge region, that elements have also has a L edge. L edge is lower than the K edge region. So, for example, it's a platinum. Platinum has platinum K edge is a more high region. However, the L edge is here about 12 kilo EV. So you can get information by using such facilities. I haven't explained about element selectivity. This right figure shows the cobalt and the nickel absorption spectrum. And so cobalt edge is about 7.7 kilo EV, and the nickel is 8.3 kilo EV. So if you tune the X-ray energy about here and here, the information around the cobalt and the nickel are separately obtained. Also, there is some of the interference. If you concomitant with cobalt and nickel, that is a little bit difficult to this region. However, we can get information about here and here. So energy is dependent of edge energy is dependent on the element. So we can get each of the element. And how to do curve fitting analysis based on the exact function was theoretically explained about here. And this formula, that is an important point. However, you don't remember, memorize it because we don't care about it. But the important point is you must calculate the coordination number, wave vector, the divider factor, distance, phase, and so on. I focused on the coordination number. Why coordination number is important for the analysis? Because how to calculate the coordination number is explained here. Of course, you don't. I am sure that you all of you know the coordination number's meaning. However, I prepared such a sheet, so I will explain about it. For example, the upper two atom fields adjacent atom number. This atom fields 3 adjacent atoms. Of course, this left part has also 3 adjacent atoms. Both bottom side of the atom fields only 2 adjacent atoms. In this case is 2, this case 2, and the center of this atom fields 1, 2, 3, 4, 4 atoms here. So average coordination number was calculated like this, and the coordination number can be 2.8. I can see because some of this part. Okay. 2.8. What does it mean? Because increasing the number of gathering, in this case 3 atoms, and this 7 atoms is I calculated 15 or like that. Then circle size is increasing and coordination number was increasing. That is finally, this is a fully coordinated case is understandable. This case, this center atom field is 1, 2, 3, 4, 5, 6. 6 is the highest coordination, saturated coordination. So finally, these two-dimensional model gives a coordination number of 6. In other words, I extended to the 3-dimensional model. For example, is using a cube octahedron in the 1 and 13, 55, 147, and then like this. This case, of course, nearest atom number is maximum is 12. So number of atoms in such particles, but cube octahedral model, 13 case is a coordination number of 5.5, 55 cases, 7.9, 140, 10, 9, 10, 11, and finally 12. In this case, different number of atoms differences means the difference in size. So cluster size was different. It means if you get a coordination number of 9, then it means 147 clusters, or like 1.9 nanometer in diameter. And it's higher, the larger number of the coordination number 10, and the diameter of about 3 nanometers. So cluster size can be obtained from coordination number. So coordination number is a very important point of the Zaf's analysis, Zaf's understandings. Okay, and the second important point of the Zane's analysis, valence estimation from Zane's can be done. This case is shown in the manganese case. Here is manganese foil and 2-valent manganese oxide, mangan hydroxide, and 3O4, 2O3, and then manganese O2. The different shape can be seen. However, this is the different edge position. Inflection point was calculated and obtained. So if you get these data, sorry, edge energy is different, and corresponding formal balance was plotted here. So almost a linear correlation between the edge energy is here, about here, and the balance of the manganese, balance 0, and 2, 2.7, and 3, and 4, like this. So you can measure your sample of the manganese oxide case. You can see your inflection point, the so-called edge energy, and calculate about the formal balance or the average balance of the manganese. It's a good point from Zane's analysis. Okay, application of the ZAFs for the development of solid catalysts. So first part, why catalyst researchers are interested in nanoclusters? At least if you have there's an idea or against this idea, so catalyst researcher must be replaced for me. Ichikuni is interested in nanoclusters is okay. So and to develop the catalyst, many elements can be a candidate for developing the active catalyst. There are some restrictions. You can see for the effect of the environment, or of course the cost and abundance and so on. Many platinum group metals have a higher activity toward many reactions, and you applied for the such a for the famous one is the platinum is famous for the fuel cell, and rhodium and palladium is famous for the automobile catalyst, three automobile catalyst. And however, they are really precious, very, very precious, and distributed unevenly. Abundance is such a clock number is very, very low. In that, on the other hand, iron base metals such as iron group metals have a very high abundance, and of course, from that reason, relatively inexpensive. Of course, abundant. Yes, I know the nickel is a good point at Indonesia. Indonesia is our largest source of the nickel in the world. I know. So if you use these base metals, then it's good for the industries. So we try to get, and of course, iron, cobalt, nickel, copper has some activity as a catalyst. However, the activity is not high enough compared to the platinum group metals. So we try to develop it. How to improve the catalyst of those kind of base metals? The answer, one with answer is a nanocrystallization. Nano size is, what is nanocrystallization? That is a good point. As decreasing the size of the particle, so the surface atom ratio was increased, like here. Number of active sites can be higher. Increase the number of active sites as decreasing the size. Here is icosahedral clusters. If you have a 3 nanometer clusters, then the surface atom ratio is less than 50%. However, if you make 1 nanometer cluster size gold clusters, then almost all the gold atom can be exposed to the outer side, can act as active species. Only here over 90%. That's a good point. That is one of the reasons. However, the important point is that this second part, active by nanosize, so-called nanosize effect. Gold doesn't have no catalytic activity before the 1990. However, 1997, Professor Halter had found these phenomena. Nanosized gold supported on some oxide has with a less than 3 nanometer gold particle shows a C oxidation activity. There is almost no activity about 5 and 6. The larger particle doesn't have such activity. However, less than 3 nanometer, there is a sudden increase in the activity. What compared to these surface atom ratio, we can explain about these phenomena. Some of the reasons, though, this is an interface between the gold and the oxide support. However, the size itself is important. This case is also the gold nanoclusters. However, without support, but we can see such information about here. The less than 3 nanometer is a key steps of the strong phenomena. High activity was observed like here. So we try to make this under part of the picture. Smaller particle can proceed the reaction. However, larger one, this is the larger one, the usual case is a very large particle. So in this case, we can get a catalysis. So smaller one is good for just a non-size effect. Okay. However, so many investigations and researches has been done for the developing the precious metal groups, platinum and gold also so strongly researched, investigated many researchers. But I try to develop the base metal nano cluster. And of course, it's a very difficult case. So drawback of base metal nano clusters. First reason is the base metals are easily oxidized compared to such a platinum or gold case. So oxidation should be taken into account. And the second point is difficult to obtain the nanocluster compared to precious metal nanoclusters. But we must answer these drawbacks. Okay, don't insist on metal catalyst. Instead, oxide catalysis will be developed. Of course, as explained, like here, alcohol oxidation is one of the good important reactions. So the oxide case is applicable, I think. And difficult to obtain, but difficult is not good word, I think. Difficult means must be overcome. So, okay, by researchers must devoted into develop such to overcome such a difficulty. We must say, yes, we'll do it. Okay. This phrase is very, students very love like this. So I usually use these phrases. Okay. And, but the usual cases, impregnation is a conventional method to prepare the catalyst. These cases distributed, this case is salt on their support, higher surface support and supported on support. Then their size was very large one. In some cases, very small one can be observed. However, the size is very, very widely distributed. From smaller one, there is very larger one. So we use a nanoparticle, colloidal nanoparticle was applied. This is metal salt was dissolved in the solvent and reduced with stabilizer. Then firstly, the produced nanoparticle growth was suppressed by a stabilizer. Then stabilized metal colloid was obtained. This was supported on support. In this case, monodispersed smaller size can be obtained and converted into the metal oxide nanoclusters. This is our strategy for getting metal oxide nanoclusters. Okay, move to the nickel oxide nanocluster case. Of course, we make such a nickel nanoclusters. In colloidal nickel nanocluster was obtained here and supported on many surfaces. This case is activated carbon and silica, alumina was applied. Okay, now the obtained catalyst was checked by a nickel cage exhaust. And you can see here, this is normalized data, and this is a fully transformed data. So lower part, you can see a standard comparison, standard materials are presented. Here, under part is a nickel metal, and the second from the bottom, second from the bottom is a nickel oxide. And obtained catalyst, activated carbon supported one, the aluminum supported one, the silica supported one is what presented here. And at first glance, very different in the Zane's region. You can see very different field. So nickel nanoparticles as oxidized even in the at room temperature, at the ambient conditions. So oxidized case was easily obtained for the nickel nanoclusters. How is the differences between the many support? We checked it about inside XRD measurement. Then high temperature was required to transform from nickel oxide to nickel. This is a reducing circumstances. The interaction between nickel oxide and support was strong in case of this activated carbon and aluminum compared to the silica. Silica case is 473 Kelvin. You can see a nickel metal. However, the activated carbon and aluminum case is only 100 Kelvin higher. was required to reduce the nickel oxide. Okay, catalytic reaction has been tried to check their catalysis. 1-phenyl ethanol to acetophenol in paratylene, and using oxygen in near circumstances as an oxidant without base additive. That's a good point. So obtained catalyst didn't show their activity for the aluminum support silica support case. Only activated carbon has a activity toward this reaction. Why such a characteristic was observed? From this analysis, no change in the chemical species was observed. Also, XPS analysis has been done. However, no change in the balances was also checked by using XPS analysis. So activated carbon may affect not only the structure of the nickel, however, directly affect the catalysis. And also the interesting feature was observed for the by washing process, the solvent differences. Catalytic solvent was different from the first point is we use a water. However, changing the solvent as methanol or acetone. And in that case, yield was very different. The catalytic performance was very different, elevated by using acetone solvent by this washing process. How comes from these differences? So we check the users for these solvent change the case. They carefully check this point. So this case, peak position, white line broadening was observed. However, almost no difference between the three solvent differences. However, exhaust function, you can see a little bit differences between them. This is not slightly declined. So it means a different oscillation period for between them. And Fourier transform data was shown here, and you can see a comparison between the nickel oxide and the nickel hydroxide. So this peak position is differed from the nickel hydroxide and nickel oxide. So the peak position of this nickel scattering is you can estimate of the ratio of the nickel oxide and the nickel hydroxide. So we get the information about it. So the acetone was used for the washing solvent. Then the nickel oxide is higher. However, water is applied to washing to remove such a ligand case. Also, the part was many parts consisted of nickel hydroxide. So active species of the nickel oxide is an important point. So to elevate the composition of the nickel oxide, using different solvent is an important point. In other words, we can see differences by using ZAS technique. Without using ZAS, we can get the information. So at this point, if we don't use about it, we can't get these goals. Okay, this is a good yield, this is a not good yield, but for reason we don't know. However, ZAS analysis revealed that the nickel oxide ratio, increasing the nickel oxide ratio is an important point. So, and the reaction mechanism was checked by using additional ZAS analysis, and by adding 1-phenyl ethanol for the catalyst and measured the exhaust and analyze the coordination number of the nickel oxygen, and reveal that without 1-phenyl ethanol, the nickel oxygen coordination about 7, However, the addition of the one phenyl ethanol, the coordination number of the nickel oxygen is increased about 1. That means nickel was coordinated with at the reaction stage these one phenyl ethanol oxygen to coordinate here, and the dissociation of the OH by nickel oxide nanocluster was observed. And after that, subtraction of the hydrogen in CH group was activated oxygen or activated carbon. That is our conclusion of these types of the reaction mechanism. The interfacial structure has an important effect of the reaction was the conclusion of these topics. And can have okay, it's time. Support substrate support. This case activated carbon subtracted alpha hydrogen. And the second question: can support subtract hydroxyl oxygen directly? So we use strong basicity with strong basicity support was applied. So we introduced the hydrotalcite. Hydrotalcite has magnesium, aluminum hydroxide, double hydroxide. So the change to hydrotalcite case, and temperature was lowered. One phenyl ethanol oxidation reaction was applied, then we can see a good reaction having a good turnover number. It means a higher activity. Highest activity, what I call selective oxidation, was achieved here in this case. Why such case is observed? This case, of course, is basic support is important. However, the hydrotalcite is the highest activity. Aluminum and magnesium is not so high. Compared to silica, very high activity can be obtained. However, hydrotalcite is the highest. In this case, OH group of the one phenyl ethanol was directly dissociated by the support hydrotalcite. Move to, and the next the subtraction of the alpha hydrogen was occurred at the nickel side. This is a different case. So by using a different support, and so we can change the reaction mechanism. In this case, we found it here, and we also found that by using ZAFS analysis. Okay, move to this second point is manganese oxide non-cross catalyst case. We introduce why using a manganese oxide. Manganese is, of course, compared to the nickel, is not familiar to Indonesia. I think nickel is important. However, manganese is very highly abundant, about the 10th or 12th in the clock, highest concentration in the clock crust. So, and also has differences in oxidation state can be obtained. In the case of nickel, stable oxidation state is only 2, and of course a metal 0. However, the manganese case 7, 6, and 4, 3, 2 is stably exist. So, if using manganese to oxidation or the dehydrogenation reaction, then these redox cycle can be easily obtained. We hope so. Should be utilized as not oxide. But in some cases, of course, manganese oxide is a strong oxidant, like this. Potassium manganese O4. But that is not catalyst. So we develop manganese as catalyst. In some case, the same protocol was applied for the getting manganese oxide nanoclusters and reducing or changing the ligand, and polyvinyl pyrrolidone was applied for the to protect these nanoclusters, and supporting the support materials applied for this the manganese colloid. And silica support was applied. First, silica support was applied for the getting manganese oxide nanoclusters. This was an XRD pattern, and we can't see any peaks about 20 weight% manganese oxide nanoclusters. At this point, we can't conclude the nanoclusters either. Oh, oops. No? Okay. This case, 3 weight% doesn't show the manganese. Of course, colloidal derived catalyst doesn't show any peaks with that silica hollow peak. So, but in conventional case, conventional impregnation catalyst shows that at a 20 weight% shows a manganese 304 peaks. So, this case impregnation catalyst has a larger manganese particles on the support. However, the colloid catalyst does not. And the checks exist to what is the chemical species or what is manganese has been prepared on the support. Then we can see colloid 20 colloid derived catalyst showed here. This case, this is a FT profile of the exhaust. And we can see the 20 weight% case, there is a little bit peak around the manganese scattering. So it has some of the size. However, it isn't large enough to detect the XRD. So also the exhaust shows show or supports the existence of fine clusters, small clusters. Finally, we use transmission electron microscopy to check the particle size. And here, a colloid-derived case was applied to measure the particle size distribution. And 3 weight% case, the average particle size is a 2.1 nanometer, very small one. Manganese oxide was obtained. And 20 weight% case is a 6.6 distribution, little bit distributed, and a larger one was obtained. Oh, okay, and move to catalyst result. Here is a result of the one phenyl ethanol oxidation reaction to get acetophenol. In this case, interestingly, colloid derived this lower part and entry 3 and 4 is the impregnation catalyst, and 1 and 2 is this colloid derived one. The colloid derived catalyst shows a higher activity than compared to the impregnation catalyst. Yes, it's okay. However, focused on these values, particle size manganese oxide on 3 weight% is smaller than 20 weight%. However, catalyst shows a higher yield compared to, but 20 weight% catalysts show a higher activity compared to the 3 weight%. Why such differences occurred? Smaller one is better, is not? So check the Zane's region of the manganese case. Then the Zane's analysis reveals that 20% case, then this composition was obtained. And 3% case, here the composition was obtained. So the important point is there are thought to be active species of these such a kind of the oxidation reaction is a manganese 4 tetravalent case, a manganese O2. So 20 weight% case is a high concentration compared to the 3 weight%. 3 weight% case of the manganese oxide is a very small size, so the desorption of lots of oxygen has occurred because the smaller one is a higher surface energy. So led to a low valence of the manganese. And there are 20 weight% case, the oxygen desorption was suppressed. So as a result, the balance of tetravalent manganese was obtained while keeping cluster size small in colloidal case. We can say the size and valence analysis are both important. Not only the size, but also the valences of these oxide case is important. So thus can you apply for these cases. And mangan valence is applicable for other support. We check it. Only a silica can be done. No. And the answer is yes, applicable for the other support. And we try to use not silica, but aluminum, also aluminum. This was a 3% case of silica and alumina, and colloidal derived catalyst was prepared, and yield was different. In this case, manganese oxide has a little bit larger than on the silica. Alumina is a little bit larger than compared to on silica. However, the catalysis was very different. 3 times higher, the higher catalytic activity was obtained. And in this case, also the higher valence was observed here in the alumina case. No divalent case and 40% tetravalent. So also applicable for this support case. The balance analysis of manganese oxide monocluster is important for understanding the catalysis. I concluded it. So I summarized it earlier. This case is what is not the important point. The take-home message is the last one. Zaf's analysis can give the crucial information for developing the catalyst. That is it. I want to say only these places. And of course, I must thank this acknowledgement has been done. And this work was done not only, of course, not only me, but also these staffs. Professor Emeritus Shogo Shimatsu, interesting. Shimatsu Sensei was retired on this spring, and Associate Professor Takahashi Hara, and in Nikkakus, Dr. Sasaki Takuro has been devoted to many data, and the manganese case is Kyoko is devoted for effort, and of course there are many part of the works was help work with University Catholic de Louvain, and Professor Eric Guignot and Dr. François Devraret, Dr. Pierre Eroy, and this was supplied to the JSP Skakenhi. So thank you for your attention.